Professor Belfrost's science class is back.
Hi, welcome back to this channel. And today we'll again discuss another concepts related to science. So here's the science tutorial for you today. Are you ready? Let's continue playing this video. Okay, I'm back here to explain about the next lesson on the same chapter, which is function. And this is the fourth video on the function chapter. Okay, let's continue from the ones that we left on the last lesson. So, yeah, okay, now we enter the subtopic of using a graph to determine whether a function is increasing, decreasing, or constant. Yep. Okay, so let me see. Yeah, we analyze from the figure 3. So this is the plot of the function x cubed minus 12x from the range minus 4 to near 4, minus 4. It's about, actually it's from minus infinity to infinity, but let's say that we cut it from minus 4 to 4. Okay, and what you can see is that the caption, this figure, this graph is increasing on the range of minus infinity to minus 2 and 2 to infinity, and it is decreasing on the um, domain of minus 2 to 2. Okay, so while some functions are increasing or decreasing over the entire domain, then many others not. So a value of the input where a function changes from increasing to decreasing is a location of what called a local maximum, and the function value at that point is the local maximum. And if a function has more than one, we say it has a local maxima. And similarly, a value of the input where a function changes from decreasing to increasing as the input variable increases is the location of local minimum. And a function value at that point is the local minimum, and the plural form is local minima. Together, the local maxima and minima are called the local extrema, or local extreme values of the function. Okay, and the local is sometimes replaced with the term of relative. Okay, but we may stick in the local in this explanation. Okay, let's see figure 4. Okay, so this is a graph of the same before, that we see that the local minimum here is shown that it is uh local minimum, it is minus 16, and local maximum is 16. Local maximum occurs at minus 2, and local minimum occurs at x equals 2. So to locate the local maxima and minima from a graph, that we need to observe the graph to determine whether the graph attains its highest and lowest points respectively within an open interval. Okay, so this is an important point. And the graph will also be lower at a local minimum than a neighboring point. So you can see here, figure 5, definition of a local maximum. So we have increasing function, decreasing function, and this observation led us to a formal definition of local extreme. So you see, a function f is an increasing function on an open interval if fb is greater than fa for any two input values a and b in a given interval where b greater than a, and a function f is a decreasing function on an open interval if fb less than fa for any two input values a and b in a given interval where b are greater than a. And a function f has a local maximum at x equals b if there exists an interval ac with a less than b less than c, such that for any x in the interval ac, fx less than fb, and likewise f has a local minimum at x equals b if there exists an interval ac with a less than b less than c, such that for any x in the interval ac, fx is greater than or equals fb. Okay, so this is important notes that you need to always take on in mind. So let's analyze the insect saber. So given the function pt that is shown in the figure, identify the intervals on which the function appears to be increasing. Okay, so we can see here, we see this is a decreasing part, this is increasing, so increasing from 1 to 3, and then from 3 to 4 it drops, and from 4 to positive infinity it also uh, goes up, increase, rise. Okay, so the interval notation is on an interval of parentheses 1 3 and interval parentheses 4 infinity. The next thing is, so the next example is finding local extrema from a graph. So graph the function of x equals 2 by x plus x over 3. Then use the graph to estimate the local extrema of the function to determine the intervals on which the function is increasing. So yeah, we have been shown the graph, so we don't need to graph it again. And we can see here what is the local extrema of the function. Local extrema means that we need to identify the local minima and the local maxima. Okay, we can clearly see that the local minima is here, okay, -4, and the local maxima is 4. Okay, so it appears there is a low point or local minimum between x equals 2 and x equals 3. Okay, so this is local minimum, and the highest point is, okay, somewhere between -3 and -2. This is the, yeah, the analysis. And finding local maxima and minima from a graph, it is very obvious. This is local minima, this is local maxima, right? And now you can see here, this is a toolkit for graphical behavior. So constant function is neither increasing nor decreasing. For identity function, it is always increasing. For quadratic function, it's increasing on the range of 0 to infinity, and decreasing on the range of -infinity to 0, and the minimum is at x equals 0. For a cubic function, it's always increasing. For reciprocal function, it's decreasing on the range of -infinity to 0 and 0 to infinity. For reciprocal square function, is increasing on the range of -infinity to 0 and decreasing on the range of 0 to infinity. For the cube root function, is always increasing. For square function, is increasing on the range of, on the domain, I mean, on the domain of 0 to infinity. And yeah, for absolute value is increasing on 0 to infinity and decreasing on -infinity to 0. Now we may use a graph to locate the absolute maximum and the absolute minimum. So you see, we need to locate the highest and lowest point on the graph for the entire domain. So what makes the previous one, local or relative maximum and minimum, to be different with this absolute maximum and absolute minimum is the domain that we take care of, or not take care of, where we take into account. Okay, if we are dealing with relative, I mean, yeah, we are dealing with certain domain, we are not considering the entire domain. But for this, we need to consider entire domain. So the y coordinates or output at the highest and lowest points are called the absolute maximum and the absolute minimum respectively. So please pay attention to the figure 13. So we can see here the absolute maximum is on f2 equals 2 here, whereas the absolute minimum here is on f0, which is -2 here. And this is the point that you need to understand. Okay, let's find the absolute maximum and minimum from this graph. So you can see the absolute maxima here is 16, I think, and minimum is at -10 maybe. Yeah. Okay, now let's go to, yeah, composition of function. Composition of function is a very crucial thing in function discussion. So suppose we want to calculate how much it costs to heat a house on a particular day of the year, and the cost to heat a house will depend on the average daily temperature, and in turn the average daily temperature depends on the particular day of the year. And notice how we have just defined the relationship that the cost depends on the temperature and the temperature itself depends on the day. Okay, so this is our beginning on the discussion on the composition of function, because it means that one variable depends on the other variables. That by using descriptive variables that we can notate these two functions. The function Ct gives the cost C of heating a house for a given average daily temperature in T degrees Celsius. And the function Td gives the average daily temperature on day D of the year. And for any given day that the cost C Td means that the cost depends on the temperature, which in turn depends on the day of the year. Okay, so let's combine function using algebraic operations. So function composition is only one way to combine existing function, and there are another way to carry out the usual algebraic on functions such as addition, subtraction, multiplication, and division. Okay, for example, we see here this is addition or summation. So double Y is the wife's income, and HY is the husband's income in year Y, and the TY represent the total income of a household. So TY equals HY plus WY, and also it's the same that we can define this one. Okay, F plus GX is equal Fx plus GH. F minus GX equals Fx minus GX. Fgx equals Fx times Gx. F by Gx equals Fx over Gx, where Gx is not equal 0. Let's dive into the example that find and simplify the function g minus fx and g by fx given fx equals x minus 1 and gx equals x squared minus 1, and are they the same function? Let's see. So g minus fx is gx minus fx. So gx is x squared minus 1, and minus fx is 1 by 1 minus x, right? So x squared minus x, and it is x minus 1. If we factorize it. But how about g over fx? It means that this is gx by fx. So gx is x squared minus 1, and fx equals x minus 1. And x squared minus 1 can be factorized to be x plus 1 times x minus 1. It means that we can eliminate the identical factors with x minus 1, and we left with x plus 1. So certainly that the functions for both g minus fx and g by fx are not the same. Next, that we create a function by composition of function. So the process of combining functions so that the output of one function becomes the input of another is known as a composition of functions, and the resulting function is known as composite functions. And you can combine these two functions by following notations. So I always say this is a dot. Okay, I don't know how you said it, but I always say dot. Okay, so if I say dot, it means that we are dealing with composition of functions. Okay, so f dot gx equals f gx. So we read the left hand side as f composed with g at x, and the right hand side is f of g of x. That the two sides of the equation have the same mathematical meaning and are equal. But you need to notice that fgx is not equal to fxgx, okay? Okay, this is the example. If fx equals x squared and gx equals x plus 2, then fgx is x plus 2 squared. It means it is x squared plus 4x plus 4, but gfx is g is x plus 2, but we substitute x to be x squared, so it's x squared plus 2. So we can only compose in one specific order, and it is not commutative. So fgx is not the same as gfx. Okay, so this is a very important thing. Okay, this one. Okay, let's dive into the next example. So using the function provided that find fgx and gfx and determine whether the compositional function is commutative in this case. Okay, so fgx, it is 2 times 3 minus x plus 1. So 6 minus 2x plus 1. So 7 minus 2x. But with gfx, it is 3 minus, in bracket or in parentheses, it's up to you, the x plus 1. It means that the result is 2 minus 2x. So for sure, this 2 has the same, has the has different, has different result, and it means that the operational function composition is not commutative. But even that, you will find out the things that sometimes the condition is commutative. It is only specific condition. It's not applied to all other circumstances. Okay, then the function of cs gives the number of calories burned completing s sit-ups, and st gives the number of sit-ups a person can complete in t minutes. Then interpret c of s of 3. So the inside expression is in the composition is s of 3, or s, I will always say s, just s3. Okay, and because the input to the s function is time t equals 3, it means that the t equals 3 represent 3 minutes, and s3 is the number of sit-ups completed in 3 minutes. And using s3 as the input to the function cs, it gives us the number of calories burned during the number of sit-ups that can be completed in 3 minutes. Okay, example 4. Suppose fx gives mile that can be driven in x hours, and gy gives the gallons of gas used in driving y miles. Which of these expressions is meaningful, fgy or gfx? So the function y equals fx is a function whose output is the number of miles driven corresponding to the number of hours driven. So number of miles equals f number of hours, right? And the function gy is a function whose output is the number of gallons used corresponding to the number of miles driven. This means that number of gallons equals g number of miles. Okay, so the expression gy take mile as the input and a number of gallons as the output, and the function fx requires a number of hours as the input. Okay, so trying to input a number of gallons will not make sense, so fgy is meaningless. Okay, as the expression fx takes hours as input and number of miles driven as the output, and the function gy requires the number of miles as the input. Okay, so yeah, when we are doing this one, it will make sense. It's very easy. Okay, now for our last lesson for today, we try to evaluate composite functions. So once we compose a new function from two existing functions, that we need to be able to evaluate for any inputs in its domain. And yeah, there are several ways that we can do this. The first is to introduce you with evaluating the composite functions using tables. For example, like this. Using table 1, this is a table 1. Okay, you need to evaluate fg3 and gf3. Okay, so to evaluate f of g of 3, that we start from the inside one. Okay, g3, find out g3, this 2, it means f2, which gives us 8. How about gf3? Start from f3, f3, it's 3, right? g3, it's 2. So actually it's very easy. Now let's start evaluate composite function using graph. So here are the steps that you need to follow when you need to evaluate composite function by using graph. Okay, I'll not read it to you, but you need to read it by yourself. So for figure 1, evaluate fg1. So first find g1. This is the inner part, right? You need to solve it first before you can dive into the outer part, okay? Then g1. G1. This is g1. Let's draw a vertical line, and you see the intersection is at y equals 3. So it means f3. Then you draw a line f3. Yeah, you see this is 6. So it means fg1 is 6. Okay, and this is the process that I showed before. Now, evaluating composite function using formulas, that when we evaluate a composite function where we have either created or been given formula, that the rule of working from the inside out remains the same. Okay, and this is the steps that you need to follow. Given ft equals t squared minus 1 minus t, I mean, and hx equals 3x plus 2, then evaluate fx1 fh1, I mean. First, start from evaluating h1. It means that you substitute this x with 1, so 3 1 plus 2, it is 5. And then f5, so you substitute this 5 squared minus 5, it is 5 5 minus 1, right? It means 20. Done. And this is your homework. Okay, yeah, I think it is enough for this video. Before I end this lesson, I want to share with you a very good quotes that Lao Tzu once said, "The journey of 1,000 miles begins with one step." That's the end of the video for today. Thanks for watching, thanks for following so far, and here's what you need to do. Please subscribe, give a thumbs up, comment, and share this video to your friend. And also, don't forget to check our website at https://science-with-exploits.uanaux.com, and I'll be back on every Tuesday, so keep watching and be thoughtful. Goodbye, see you.